Hi everyone, this is Mathieu Cocheteux with Université de Technologie de Compiègne and CNRS from France. I'll now introduce PseudoCal, our novel camera-to-LiDAR extrinsic self-calibration method. First, what is sensor calibration? Well, there are two types of calibration. Intrinsic calibration, which is about correcting an inherent bias in a sensor, such as a default in the lens of a camera, to improve the output. And extrinsic calibration, which is about finding the spatial transformation between two sensors to allow sensor fusion. This work will focus on extrinsic calibration. So, why would you use machine learning? Is there something wrong with classic methods? With machine learning, we're trying to achieve some kind of universal model that gets as an input a decalibrated sample with incorrect calibration parameters, and to get as an output correct calibration parameters, which give good projection of the LiDAR point cloud onto the image frame, as you can see on this image. Advantages of machine learning compared to traditional methods are that it offers a better accuracy because it does not rely on any target or encrafted features. It also offers a faster process because it does not require any data acquisition by humans, but also the computation itself is faster. Finally, machine learning offers a stronger resilience because it can be done online without any human intervention, meaning it can be done at any time when the vehicle is operating. Here is a typical architecture from the state of the art. As you can see, there are two branches to extract features from camera and LiDAR. On the LiDAR branch, you can see a projection step, which takes the LiDAR information from 3D to 2D by projecting it with tinit, the initial calibration parameters that we want to fix. Finally, the features extracted from both modalities are matched by a vision backbone, and the correct calibration parameters are regressed by the head. This works, but these methods have some limits. In this simplified illustration, I wanted to highlight the projection step, which in my opinion is the most important limit to the current state of the art, because it requires an initial approximate knowledge of the true parameters. This limits the field of application to only recalibration, and not full calibration, where we do not have any information about the actual parameters. Finally, by projecting 3D information into 2D, it wastes most of the LiDAR data. Now, imagine this situation where you have a LiDAR and a camera sensor. In orange and blue are their field of views, and the object they can perceive. Now, imagine that we apply some decalibration. If we tried to recalibrate using a state-of-the-art method, we would project the LiDAR information into 2D, restricting its field of view. As a result, we would not be able to perceive the orange pentagon object through the LiDAR. This means there would not be any common object perceived by the LiDAR and the camera. Thus, we could not perform the calibration. Now, by using our novel method PseudoCal, we work directly in the 3D space and use the full LiDAR point cloud. This means that we do not require any initial parameters because we do not have a projection step. As a result, we can perform full calibration and not only recalibration as existing methods. For example, in this scene, working in 3D is that we're able to perceive both pentagon objects. The network will then be able to match them and perform the recalibration. Now let's zoom in into our method with our novel module pseudo-LiDARs. Unlike existing methods, which try to take LiDAR information into 2D, we bring the camera information into 3D. For this, we first use a depth estimation method. This depth map is then projected back into the 3D space as a pseudo-LiDAR point cloud using camera intrinsics. Finally, a pilar sphere net encodes the point cloud as pilar spheres. The LiDAR point cloud is also encoded the same way. Features are then matched by a vision backbone, and a head regresses coarse estimation of the parameters. Let's zoom in into the pilars. You can here see a visualization of the pilars in our method. You have to imagine this as some kind of bird's eye view, where you can see from above the vehicle. Walls appear here as some kind of lines. You can see common objects, such as walls, in red and blue. This is the type of information that the network is going to be able to learn to match both modalities together. Advantages of using pylars as a representation of a 3D space are that it is a compact representation for sparse point clouds, like those of LiDARs and pseudo-LiDARs. Furthermore, it is also compatible with usual network layers, which is really convenient in terms of engineering. Our novel pseudo-pylars module works in 3D without initialization and is able to regress coarse parameters. However, we want to refine them to get closer to the state of the art in terms of accuracy. This is why we add a refinement cascade made of 2 refiners. This refinement cascade first receives the coarse estimation from pseudo-pylars. It then passes it to a first refiner, which refines it further, and passes it to a second refiner, which regresses the final value. Each Unical-based refiner is trained on an increasingly narrower decalibration range and specializes on its own training range. This is how it is able to refine further value. Now, here are some quantitative results on the Kitty dataset. As you can see, our method is competitive with state-of-the-art in terms of absolute error. However, some methods such as LCCNet offer an even better accuracy by using multiple scenes and an iterative refinement. While this could have been implemented in our method, this is not the objective of our work. With PseudoCal, our main contribution actually resides in the decalibration range columns. Unlike existing methods, which work in 2D, we directly work in the 3D space. This means that we're not bound by the same limits. You can observe that all existing methods max out at 20 degrees in all rotation axes. This is because with a decalibration greater than 20 degrees, there is no common information left between the two modalities. This means that this method would fail. However, by working in the 3D space and using the full LiDAR point cloud, our method is able to bypass this limit. This is how it can still work with decalibration greater than 20 degrees. Roll, we could technically go further and have achieved success with decalibration of up to 45 degrees on roll and pitch. By using such a large decalibration range, we try to simulate most possible locations for a sensor in the context of intelligent vehicles. With minus to plus 180 degree decalibration on the y-axis, we simulate an orientation of the sensor toward any direction around the vehicle. This training enables us to do a full calibration and not just recalibration as existing methods do. Here are some qualitative results on the Kitty dataset. You can see samples from 2 scenes. On the first row, you can see the input, where a large decalibration has been applied. On the second row, you can see the output of our pseudo-pylars module, which gives a coarse estimation of the calibration parameters. Finally, on the third row, you can see the output of the full method PseudoCal, which achieves near-perfect calibration. We can zoom in to better distinguish the improvement made by the refinement cascade. At this point, we have achieved our final calibration. Thank you for your attention.
Do not hesitate to drop us an email.